Good afternoon. Welcome to AP Statistics. We're beginning Unit 8 today. The Unit 7 test, I expect, will be graded by block day. If you haven't taken that, so try to take that block day. Now, I think there's only 2 units in this course that are single chapter units. Unit 2 covered only one chapter, that was chapter 6. This unit, Unit 8, covers only one chapter, and it's chapter 18. If you read no other chapter in the book, read chapter 18, because in chapter 18 we learned the fundamental theorem of statistics. It's not the same thing as the Pythagorean theorem of statistics, which was a yogurt day thing. It's a yogurt day thing. But today it turns out that the Pythagorean theorem of statistics helps us prove the fundamental theorem of statistics. So there's going to be a revisiting of yogurt day. It's like, we're going to drink deeply from the Chobani 32-ounce yogurt.
Is it gloppy?
It tends to be less gloppy over time. It kind of smooths out, especially if it's not in the freezer. So let's begin. The fundamental theorem of statistics. Read chapter 18. That's your only homework between now and block day, is to read chapter 18. So here we go. On your word picture quiz, I would like to fill in, just to make this fresh, down to problem 5. Please fill in A, B, C, D, E, F. We're going to put a 19, choose 5 here. Break this up into 3 sections. We're going to go 0.55 and 0.16 for that part. This will be given G of 0.45, probability of success of 45. Find the probability that X is greater than 11. And then down here, given that we have, let's say we're taking a sample of 10 people, we're going to ask them, are you going to vote for Donald Trump, yes or no? Suppose the true proportion, and only God knows what the true proportion is, are going to vote for Donald Trump. But suppose it's 0.48. Even if he loses the popular vote, he might still win the electoral college vote. But suppose that, what's the probability that X is greater than, not greater than or equal to, but greater than 7? So that's just for review. Now, today we're going to be filling in the word pictures for 7 and 8. And to figure out what's going on with the central limit theorem, and this title right here is actually condensed. Model of sampling. The IMG is what it takes a lot of work for me as a teacher to get across. It's like, what's the difference between a sample, a distribution of samples, and a sampling distribution? So I've thought about this a lot over the years. I feel like I finally have a plan for how to make it clear what a sampling distribution of p hat, which is a sample proportion, is. So word picture 7 and 8 on your handout. There is a concept. It's just blank. This page is to build up the 5 layers of a sampling distribution model. Underline the IMG, because when you see IMG after sample, that tells you, that's a signal that we're talking about the fundamental theorem of statistics. That IMG is such a little detail that students often, it blows past them. No, that's a huge signal. So let's take some time to build this up from what you already understand to this brand new concept, which is the subject of the fundamental theorem of statistics. First of all, the sampling distribution concept, which is like way out there at this point, no, we're going to get to it and understand it. It's based on the idea of a sample. So first, the first layer in understanding the fundamental theorem of statistics is understanding what a sample is. Imagine that we take a sample of 10 people and ask them, yes or no, are you going to vote for Donald Trump in the election? Now, today there's a primary election in New Hampshire, so the Democrats are trying to figure out who's their candidate going to be.
Field of burn.
And so it's like, it's a big deal. And probably a lot of you, you'll probably be 18. Are you planning to vote in November's presidential election? It's gonna be a big deal. So you're all of you are gonna either vote for Trump or you're gonna vote for someone else. Or you might just vote present. I don't know what you're gonna do, but you're gonna go to that voting booth. And, but between now and then, every day between now and the presidential election, first Tuesday of November, people are gonna be taking samples to try to get some sort of look into a crystal ball into what's gonna be the outcome of that election. And suppose in one sample of 10 people, they say, yes, I'm gonna vote for Trump. No, 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 yes, yes, no, yes, 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 no. So we got 2, 4, 6, 8, 10 people. So we have 6 yeses. So this is 6 yes. What was the sample size little n? And what was capital N? Well, in this case, little n, sample size was 10. Capital N is the true number of people who are going to vote. Usually in a presidential election, you get somewhere around 160 million people are actually going to vote. And I mean, even that is, we don't know for sure what capital N will be, but it's usually approximately 160 million. Okay, so that's a sample. Layer number 2 is a sample proportion. Now, actually, the difference between a sample and a sample proportion is the difference between word picture 3 and word picture 6. When it comes to just samples of a binomial situation, take a look at word picture 3 again, take out that other document, have it going side by side. I mean, that is a binomial distribution. True possible outcomes, yes or no. The probability P is count 10, little n is less than big N. Suppose it's a random sample, so it's representative. We're looking at a fixed number of successes. In this case, it was 6. 6 was the fixed number. So the mean of the variable x, which is defined as the number of people out of 10 who will say, yes, I'm going to vote for Trump, was, what was this formula? NP. It was NP. And what was the standard deviation?
Root of NPQ.
NPQ, that's right. So we're going to connect word picture 3 to word picture 7 today. 3 connects with 7. Okay? Now, this is mu sub x, comma sigma sub x. No, that didn't happen.
No.
It did happen, Mr. Royce.
Not the
We're locked down. No, it's not a lockdown. We're just, the page is locked down, so that won't move. You're free to roam about the cabin. Okay, so turns out that we're building up the concept of a sampling distribution, and we've
is that
made
right, Mr. Royce?
What?
Is that right?
That's wrong.
Yeah.
Pretty sure it was.
Isn't
I thought it was.
I thought it would be NP.
And that
National
one was
Public?
P up there.
National
Like that.
Public.
I thought that was like
But
an
if
N
you
and a
put in the
P,
bottom
and that one up there
of
was
the
a P.
National Public.
Radio.
So you wrote it down for me yesterday.
Oh,
and
yeah.
That's what I was
So
studying.
mu sub x?
Oh no, I'm
yeah,
talking
yeah.
about the little like
No,
green
no,
parenthesis
it's cool.
thing. Isn't
Oh.
that just income?
Right. I was thinking, I'm glad you caught that.
Yeah, I got
'Cause,
you.
yeah, it's just NP, just NP.
Open,
Yeah.
no cap.
Yeah, good. Now I see why people are like, what?
I was a little out there.
Okay, thank you for
Don't worry.
correcting me on that.
Doing that.
So that's a sample. And
Go work out.
the sample that produces a number that can be modeled by the binomial distribution of x. Now, let's leap from a sample to the next layer, which is the sample proportion. Sample proportion. Now, it turns out that you can change a sample into a sample proportion by just taking x, the number of people who said yes Trump, divided by n. In this case, 6 divided by 10 is 0.6, and there's a symbol for the sample proportion. It's p hat. It's not p predicted. If it's like y hat, that's predicted y. But there is a sense in which p hat, which means sample proportion, is a prediction of what the true proportion will be. Only God knows what the true proportion of
That's
people who are going to vote for Donald Trump on the second Tuesday in November is. Now, in chapter 18 is a weird chapter because in chapter 18 we peek behind the curtain and we see what only God knows. We see the true proportion, and we see also the true means. After chapter 18, once we hit chapter 19 for the rest of the course, then the curtain closes and you never know the true proportion. You can only approximate the true proportion with the sample proportion. But chapter 18 is a theoretical chapter in which we see behind the curtain. So suppose that the true proportion is 0.48. Okay, but so this sample proportion was higher than the true. This sample proportion is higher than the true proportion. Some of the samples will be less than that, but that's a sample proportion. Now, next let's look at the distribution of sample proportion. So the third layer in getting to where we need to be to understand what is that ING all about on the sampling. We don't have the ING on there yet, but we are going to look at a distribution of sample proportions. Distribution of sample proportions. And this is not too hard to pull off because every day between now and the first Tuesday of November, is it first Tuesday of November? Yeah, it's got to be first Tuesday of November. They're getting representative samples and they're taking X, the number of yeses over N, they're getting P hats, and those P hats can be distributed. In fact, here's an example of what a distribution of sample proportions would be. Here we got 0.5, 0.6, 7.8. The highest the sample proportion can be is 1, 4, 3, 2, 1, 0. And so we came up with the sample proportion. Let's represent it by a table tennis ball, and let's put it right at 0.6. So that's our first sample. Now let's take another sample of 10 people. And how many yeses were there? 4 yeses divided by 10. So next sample, we have 0.4. And suppose we're always, out of 10 people, it'll always be rounded. It will never be 0.55. So maybe every one of these table tennis balls represents another survey, another result, and we get a distribution of sample proportions. So might be one sample where all 10 of them, no, I'm not voting for Trump. So that's that tennis ball. That's a sample proportion of 0 out of 10. I have a 9 out of 10. But
Alabama.
it's like, so we see a distribution, and it could be set up, it would look like a histogram. Sometimes a histogram will amount to a distribution of sample proportions. You could do the same thing with sample means. So now, the fourth layer. Here's where we add the ING. We're going to move from a distribution of sample proportions, which is always a finite number of table tennis balls. Once we add the ING, then we move from physical reality to, it's still reality, but it's non-physical reality. It's the realm of ideas. Ideas are real. They're just not physical. Ideas have consequences. What you believe, your beliefs are real and they have real consequences, but they're just not physical. Ideas are not physical. Let's look at a sampling distribution of sample proportions. Layer number 4. Sampling, underline the ING. Sampling distribution of sample proportions. Now, a sampling distribution of sample proportions is a mathematical model. It's an idea, it's theoretical. And so instead of a histogram, it's a smooth curve. And it has a mean, and that mean will always be the true proportion. In this case, P. In this case, it's 0.48. And it also has a standard deviation. It has a mean and a standard deviation. Its mean is called the mu sub p hat, is the true proportion P, and it has a standard deviation, sigma sub P hat. We pronounce this the standard deviation of the sampling distribution of sample proportions is, and there's a formula for this that we're going to derive based on word picture number 3. So hold off on this one. This one's fairly intuitive, but the fifth layer, layer 5, since we have a sampling distribution of sample proportions, and this is foreshadowing it right here, we can then look at a model of the sampling distribution of sample proportions. And that's the fifth and final layer. The central limit theorem, which is the fundamental theorem of statistics, is all about the normal model of the sampling distribution of sample proportions. So to really make this the full-fledged thing here, there is a normal model of the sampling distribution of sample proportions. So that's an equation, essentially. It's basically, I mean, it's the equation of the curve. It's the equation of the sampling distribution. And that equation can be specified with the mean and proportion. So let's go back to word picture 7. Let's fill this in. Sampling distribution of sample proportions. A normal model of the sampling distribution of sample proportions. Just FYI, notice how they trimmed it down a little bit. They compacted it. Instead of normal model, they said model. But it is a normal model of the sampling distribution of P hat. Stands for what phrase? Sample proportions, not the true sample proportion. So the mean of the sampling distribution of sample proportions is the true mean P. Now it's a mouthful. You're expected to use your mathematical symbols precisely. So is that hat above the P dark enough to show up on your paper?
Oh, barely.
When I say go, I'd like you to begin, I would like you to say, the mean of the sampling distribution of sample proportions is the true proportion. Ready? Go. The mean of the sampling distribution of sample proportions is the true proportion. Now,
Can you say that one again?
yeah, let's do that one again. When I say go, I'd like you to say the mean of the sampling distribution of sample proportions is the true proportion. Ready? Go.
The mean
Of the sampling distribution of sample proportions is the true proportion. I didn't prove it for you. I could have proved it. Here, let's prove it. How do you turn, well, first of all, in a sample of 10 people, what's the expected number, what's the formula for the expected number of people who will vote for Trump? It's NP. We expect that there will be NP people voting for Trump. How did we turn that number 6 into a sample proportion? What did we do to the number 6 to turn it into a sample proportion?
Divide by how many people?
Yeah, we divided it by 10. So if you divide by n, take the NP, becomes P. So that's how you can take the mu sub x from word picture 3. It's like, okay, that's just a number. To turn a number into a proportion, you divide it by the total NP over N, so that's where the P came from. Now, to get the standard deviation of the sampling distribution of sample proportions, we're going to take the standard deviation of the number of people who say yes, which is square root of NPQ, and let's do that derivation in the upper margin here. It's okay, just for scratch work. So this is the mean of the sampling distribution of sample proportions is NP over NP. Okay, so let's look at the standard deviation of the sampling distribution of sample proportions. Imagine an infinite number of samples. Well, what we do is we take the square root of NPQ and divide it by N. This can be simplified. It's the square root of n times the square root of p times the square root of q. Since there's all multiplication on here, the square root of the product is the product of the square roots. And guess what we do? We're going to rewrite n as, with your permission, the square root of n times the square root of n. Do I have your permission? If not, we just have to stop and go to Starbucks or something, or Stars and Bucks. We can go to Stars and Bucks.
Stars and bucks.
I have your, thank you for giving me your permission, so we don't have to taste that awful coffee at Stars and Bucks. We can just stay here and learn more. And drink more of that gloppy Chobani yogurt. So, the square root of n's cancel. So we have square root of, we can put them all under, house them all under one square root. So here it is, square root of pq over n. Right? Now, some of you on the, watch out, some of you are doing like your square roots. It's like you think that this would, you're not housing the entire fraction under the square root symbol. This gets, I took off like 1/10 of a point if you tried to pull this off. When you were doing, oh yeah, for standard deviation of a geometric model is a square root of q over p squared. Some of you put the square root, like you meant it to be this, but mathematically this is different, so you've got to house the entire fraction under the square. It's got to be this. So here we go. The standard deviation of the sampling distribution of sample proportions is the square root of p q over n. So we're not just like blindly memorizing formulas. We're seeing, oh yeah, this is connected to word picture 3.
Is that the
Okay.
fundamental theorem of statistics
No.
right there?
No, but the fundamental theorem of statistics, also called the central limit theorem,
Oh, okay.
is it addresses these two word pictures. In fact, it's actually addresses, okay, so let's get these symbols up here. This is mu sub p hat, comma, sigma sub p hat. Now, let's fill in these other blue and one blue, two greens. Now, we're gonna have to decide what's the checklist for launching this model, thinking of it as a model rocket. Okay. Now, in order to pull this off, in order to press launch, there's two assumptions that you need to be justified in making. Some of you are getting nervous. Wait, Mr. Royce, you want me to assume something? Independence assumption. My parents told me never assume. My parents told me that if you assume, then, and then they start saying things and using a word they say, oh, my mom uses that word. Is this allowed? That's wrong. You can't say that. But they say it anyway because they're trying to get this message across. Maybe this has happened to you. Have you ever had this speech from mom or dad or mom and dad where they talk about not assuming? Has anyone ever had the don't assume speech?
In Polish.
In Polish? Yeah, so it must be spelled differently in Polish.
Here, give us a little sample.
Does the speech in Polish still have the same oomph?
No, it doesn't have the same oomph.
Oomph. Yeah, anyway, so, but you know what? You can actually be clothed in your right mind and make an assumption. Let me tell you that scientists, they make assumptions when conditions are satisfied. So there is a condition, there's only one condition, we'll call it C1. C1 for making the independence assumption. If you're afraid you're going to forget the IA stands for independence assumption, then make a note to yourself somewhere. And there are two conditions for the other assumption, which is the sample size assumption, SSA, the sample size assumption. And that's C1, we'll write here condition 1, C1, and C2. So think of using a normal model for this. Wait, hold on, wait, friends, let's stay focused. Let's stay focused.
One's for I and one's for S.
This is independence assumption, this is condition 1. Sample size assumption has two conditions, condition 1 and condition 2. Now, condition 1, in order to be justified in making the independence assumption, you need to have either an SRS, a simple random sample, those 10 people who you asked, are you going to vote for Trump, yes or no? It should be an SRS, a simple random sample, or an RS, a representative sample. If either of those two are met, simple random sample, if that condition is met, the sample is simple random sample or a representative sample, then you are justified in saying that those 10 people's responses are independent of each other. And also things like, we'll ask them privately. We're not going to let their friends know what they said during the survey. We don't want them to be influenced. We want this to be independent. Now, the sample size assumption, if you think you're going to forget that SSA is the acronym for sample size assumption, then make a note to yourself somewhere. But the sample can't be too big of a sample. It can't be more than 10% of 160 million in this case. If you think you're going to have so 10% of 160 million is 16 million. If you're going to sample 16 million people or more, that sample is too big. It's just, in the second course in statistics, if you decide to take that, you'll find out why it's 10%, not 15%. We cut it off at 10%. Yeah, question? Yeah, if you need to go ahead and just watch the video starting at 25:44 to find out what you missed. All right, so friends, the sample can't be too big. Condition 1 is that 10 little n is less than big N. That's 10 little n is less than big N. We've seen that notation before. It's a 10% condition. The sample can't be too big. It's got to be 10% of the population less, but it can't be too small either. And to make sure that condition 2 is to make sure the sample is not too small, we've seen this one also. NP, the expected number of successes, has got to be greater than 10. And NQ, the expected number of failures, has got to be greater than 10. Now, we know P and Q simply because theoretically we're in chapter 18, we're still peeking behind the curtain. We know the true proportion P. Otherwise, we wouldn't be able to use these formulas. So we're going to have to modify this once we get to chapter 19. Chapter 18 is a theoretical chapter on the central limit theorem. Okay, so now we have that. Now let's go over to what if instead of looking at a sample proportion, what if our survey is all about trying to find the true mean until we get a sample mean? What if we were trying to find out what is the true average height of a human being? And so we sampled 10 people. And we, instead of asking them, are you going to vote for Trump? Yes or no? We say, can I measure how tall you are? And then, so stand up, stand up. Stand up straight. You can't be leaning on the wall. You can't be leaning on the wall. We're going to measure how tall you are, and then we're going to average these 10, and we're going to get a sample mean. And guess what the mean of the sampling distribution of sample means is going to be? It's not the true proportion. It's the true mean. It's the true mean. So instead of looking at the sampling distribution of sample proportions, word picture 8 is about a sampling distribution of sample means. Maybe we take 70 samples of 10 people. We measure, for each sample, we get a sample height, X bar. And the mean of the sampling, we imagine is a sample of an infinite number of samples, or a distribution of an infinite number of samples to make it a sampling distribution of sample means. Now, any guesses as to what the standard deviation of the sampling distribution of sample means is?
That's a great question.
Hello?
Hello.
I don't know.
You don't know?
No.
This requires yogurt day. To get this one requires
Yeah.
the Pythagorean theorem of statistics. Yes, yes. So let me just derive it for you. It's not a proof of it, but it's an indication of what it is. In fact, you know what? Here, I'll tell you what it is, and I'll show you why yogurt day gives us confidence that it's the true standard deviation divided by the square root of the sample size. That seems like, where'd that come from? You're just making this stuff up, Mr. Royce. No, if you think about yogurt day, don't just believe me, believe the yogurt. Believe the yogurt. The yogurt is speaking to you. Are you listening to the yogurt? Okay. The yogurt has a message for you today. So, yeah, what you missed here, welcome back. We learned that now we're going from sampling distribution of sample proportions. Now we're looking at sampling distribution of sample means. Imagine, Lydia, that we're trying to find the true mean of a human being. And so we take a sample of 10 humans, and we measure them. We get a sample mean, X bar. And then we imagine, let's say 70. Let's take 70 samples. So we have a distribution of 70 X bars. And then imagine an infinite number of samples of size 10. That would be the sampling distribution of sample means, and here's a normal model. The normal model of the sampling distribution of sample means has a mean of the true mean. So just to make sure we're all together, when I say go, I'd like you to say the mean of the sampling distribution of sample means is the true mean. Ready? Go. The mean of the sampling distribution of sample means is the true mean. And I also asserted, and this part, Lydia, we're going to need Yogurt Day to prove this, or to give us confidence that this is true. It's not a proof, but it is an example. The standard deviation of the sampling distribution of sample means is the true standard deviation divided by the square root of the sample size. So here we go. Here's how Yogurt Day gives us confidence that this standard deviation formula is true. Would you please imagine for a moment that we have, suppose we have a true mean human height of 75 inches, okay? So suppose that's the true mean height. Suppose the true standard deviation is 4 inches. Or suppose you're on a planet where the true average height is 75 of all these creatures of a particular species. And we'll say 75 inches and 4 inches, okay? Now, suppose that X represents the height of just one person, the height of a randomly selected person. So capital X represents height of a randomly selected creature. Okay, we're on another planet, height of randomly selected creature. Okay, so suppose we take a sample size of 3. How would we model the average of those 3 heights? I think we would take the first height, second creature's height, third creature's height, we would divide by 3.
Yes.
That's how we would do it. And if you wanted to find the standard deviation of that sample mean, I think based on what we learned on Yogurt Day, you would first of all imagine x1 over 3 plus x2 over 3. So this is like putting this height, it's like yogurtizing it by a factor of 1/3.
That's great.
Instead of multiplying by 3, I'm just going to take the standard deviation of x1 and divide it by 3. Instead of multiply by 3, I'm going to yogurtize it by a factor of 1/3. So here, I think, remember, the standard deviation is 4. Check this out. I think the standard deviation would be the square root of the sum of the variances. The variance of x1 over 3 is going to be 4 over 3 squared. Standard deviation squared. The variance of the second, or x over 2, or x2 over 3 will be 4 over 3 squared. 4 over 3 squared. And using algebra 1, I can combine like terms, blob plus blob plus blob. I didn't say glob. We're not talking about globs of yogurt. We're talking 3 times 4.
What does blobs mean, Mr. Rose?
Blob just means item. Item plus item plus item. So now I've got 3 of these things. But then doing the basic, it's like 3 times 4 squared over 3 squared. A pair of 3's cancel. And so I get the square root of 4 squared over 3, which is 4 over the square root of 3. It's standard deviation over the square root of the sample size. Is that something? So the standard deviation of a sample mean, yeah, let's give mathematics a hand. Is mathematics a person? Okay, so
You can, Mr. Royce is smart enough to rationalize that,
I
Dan,
apologize. I
okay?
apologize.
wait, to rationalize what, from here to here?
No, from the, because you can't have a square root in the denominator.
Yeah, you
Like,
can. You can. You can rationalize it. Like, for example, if someone says, rationalize this, then you can say, okay, I know how to rationalize this, but what if you are not required to rationalize? Guess what? In statistics, we're not required to rationalize the fractions. We can leave the square roots in the denominator.
This is guys. This is
Dan, I
good.
got your question.
All right, so now we see, I mean, in general, it's going to be the standard deviation divided by the square root of the sample size. So now, even though that's not a proof that it happens every time, I gave you some indication of the connection between this formula and the Pythagorean theorem of statistics. So,
Yeah.
there we go. So this has, okay, we're actually we're just about to the point where we can say what the fundamental theorem of statistics is. In fact,
Yeah,
there's
we
3 statements to it. And the first year they did an AP test for statistics was they did a trial year in 1997. So it's like the first year where it was like really offered, a lot of people took it, was 1998. And in 1998, question 1 on the free response was, what is the central limit theorem? Give all 3 statements. And so you just had to write the following 3 statements word for word. It was in the, and so let me give you the first statement of the central limit theorem. The first statement verbally expressed is the mean of the sampling distribution of sample means is the same as the mean of the population. Let's practice saying that. Let's say statement 1 of the 3 statement central limit theorem. When I say go, I want you to say
Where
the
would you like
mean.
us to put this, Mr.
Just, I
Williams?
mean, you can write down somewhere. I mean, it's written down.
Okay,
It's
great.
written down. Well, believe me, this is like the focus of Unit 8.
Also,
and-
we'll have it.
And we're basically going to be practicing this every day this week. So this is going to be, so you'll get lots of practice. For now, let's just practice saying this, shall we? Okay, so let's just practice saying this. That was off camera. That was an off-camera event that just occurred. When I say go, I want you to say out loud and in unison, the mean of the sampling distribution of sample means is the same as the mean of the population. Ready? Go. The mean
of the sampling distribution of sample means.
It's the same as the mean of the population. Let's try it one more time. Ready? Go. The mean of the sampling distribution of sample means, let them hear you in the library, is the same as
The true,
the mean of the population. Okay. Or if you say the true mean, that's fine. But say the mean of the population for the purposes. So now the next one, literally, I mean, to let them hear you in the library, you'd have to be like this. You'd have to be like, the standard deviation of the sampling, you know, that's what it would take. That's the kind of projection it would take, okay? So when I say go, I want you to say,
Is that what you want?
when I say go, yeah, I want you to
That's a
let them
challenge.
hear you in the library.
I need a better view.
I would take off my glass.
I want you to say the standard deviation of the sampling distribution of sample means is the same as the standard deviation of the population divided by the square root of the sample size.
That's kind of long.
I know it's long, but it was question 1. They wanted the words. They wanted it word for word. They wanted it stated verbally.
Isn't it multiple choice first?
Question 1 on free response.
Oh.
Question 1 on free response was to state the central limit theorem, all 3 statements verbally. So try it. Ready? Let me hear you in the library. Go. The standard deviation of the sampling distribution of sample means is the same
As the standard deviation
of the population,
Divided by
the square root of
the
sample size.
Sample
The
size!
That's pretty good, okay?
Did they heard us in the library?
They may have. That was pretty loud. So you can go and you can take a survey. So you can take a simple random sample. Simple random sample, 5
Not
people.
convenient.
What proportion of the
Never
people,
convenient.
what proportion? We want to estimate the true proportion of people in the library who heard us say that the sample distribution.
Where did that actually go?
At the standard deviation.
What was that they didn't?
Oh, crap.
Because there was no one at the front tables, so I had to go like farther back.
Dang it.
Devin, maybe next year. Maybe
It
next
wasn't a
year.
convenient
Okay?
sample. I took the sample of the random. Friday.
Now, when you read chapter 18, you will see that there is a version of the central limit theorem.
No, you're good.
I forced it.
So, yeah, if this is important, you will see in chapter 18 that there's a version of the central limit theorem for the sampling distribution of sample proportions. However, when people are talking about the central limit theorem, there is a preference for the sampling distribution of sample means. So this is the one that they wanted on the AP test. was the central limit theorem as it applies to the normal model of the sampling distribution of sample means. Okay, now, before we fill in the conditions, there is an independence assumption and sample. And by the way, there are three statements. We did statement 1, which had to do with center. Statement 2 was spread. Statement 3 has to do with shape. So the three statements have to do with shape, center, and spread.
Ooh.
Shape, center, and spread. We did, so that whole shape, center, and spread stuff that we're doing, that was all preparing you for
this?
the central limit, the fundamental theorem of statistics. Center is mu, spread is sigma of the square root of n. Shape is
Normal.
it's a bell curve shape.
Yeah,
So it becomes more and more normal. But as a sample, so the shape is actually not normal for small sample sizes, but the shape becomes more and more normal as the sample size increases. And that is that's the sort of thing that that is actually the most surprising part of this, because it doesn't matter what the shape of the underlying distribution is. The underlying distribution could be trimodal, but the shape of the sampling distribution of sample means, yeah, if only the camera had been on that student who once I said, it doesn't matter what the shape.
It was dead, by the way.
If the underlying distribution is trimodal, or it could be, I mean, it could be like just tall on one side, but the sampling distribution, the shape of the sampling distribution of sample means will become more and more normal, even if the underlying population is as non-normal as, and that's, without that, if it's so counterintuitive.
That's not cap.
But you just can't do statistics without that.
Yeah,
So we'll continue. Read chapter 18. Chapter 18
Chapter 18 due tomorrow.
for block day. For block day, you are dismissed.